Thank you. Last night at dinner, it was claimed that Americans don't dress very well, so yeah, I decided to dress up a little today. Okay, so let me remind you what we discussed last time. Okay, so we have some polytope in Rn that we care about. And by the way, I never lecture in a jacket, so I don't know what happens. If if at some point I lean against the board and I'm covered in chalk, try not to laugh, I guess. This is the best I can hope. Okay, so we have some polytope we care about, and then we define this parameter, sort of gamma bar of P, to be the minimal number of facets in any lift of P. Okay? So just to remind you what it means, we look for some polytope Q upstairs that projects to P, that linearly projects to P downstairs, so that P has a very small number of defining inequalities. And the number, the minimal number of defining inequalities you can get in any polytope that projects to P, that's this parameter. And the reason it's interesting is because, well, generically, interior point methods can optimize over a polytope, optimize the linear functional over a polytope in time, which is polynomial in this number of facets, in this gamma parameter. Okay? And it happens to capture a very large section of sort of the use of mathematical programs to capture 0, 1 polytopes. So this is an interesting notion. Maybe one thing we didn't see enough of last time, so I'll give some exercises for the afternoon now, is that you can think about these lifts sort of operationally, and not just in terms of the geometry of something projecting to something else, but once you have some polytopes you care about, you can think about this lift, right? So this is in a higher dimension. This is in some capital N. This is our little n. You can think about these extra dimensions as new variables that help you in expressing whatever combinatorial problem you want. Okay, so here's an exercise. I'll give actually two, and the second one is sort of extra credit. I don't know, because it's more difficult. So if we define the bipartite matching polytope, so I'll be a little bit informal here. This is the, let's do it here. This is the convex hull of bipartite matchings. So, okay, perfect. Matchings in the complete bipartite graph in, say, K, N, N. And just so it's clear, this is sitting inside n squared dimensions. Right? We have K and N. There's n squared possible edges. Every point, every vertex here will choose n of those edges that correspond to a perfect matching. So the first exercise is just to show that this, let's see, is at most, I think it seems like n squared is the correct answer. Okay, n squared. Okay, and so when you doing this exercise, okay, I'll even for this one just give the hint. But the right way to think about it is the connection that people see in the first undergraduate algorithms class between ST flows and perfect matchings in bipartite graphs. So these extra variables you'll need to add are flow variables. And then one can, by adding n squared extra variables, one can express this using only n squared inequalities. Okay, so this is one example. Let me know if that didn't make sense. And the second one, which is a bit more difficult, is the spanning tree polytope. So this is the convex hull of indicators of spanning trees in the complete graph. Spanning trees in Kn. And again, just to make sure we're on the same page, this is in n choose 2 dimension. There's n choose 2 possible edges. Spanning tree will have, the indicator, the vertices here will have n minus 1 of those edges representing expanding trees. And then here's the more difficult exercise, that actually this one, so I guess I didn't say it, but both of these, the gamma value for both of these polytopes is exponential in n. Right? These polytopes, the bipartite matching and expanding tree polytopes have exponentially many facets. But the point is that by adding some extra variables, you can write them as the projection of polytopes with only a small number of facets. Because you get all of the odd set. Yeah, this is true. Let's see. It's certainly still true. It was the easier of the two exercises. Yeah. Does anybody see a way to make the problem more interesting? Could add. What's that? Yeah. Non-bipartite makes the problem very difficult. In fact, impossible because of a result of Rothfuss from last year. Okay, so this one is easy. You can do it anyway. Okay, this one still stands as something which is non-trivial. But then but if this is the exercise, I should give a hint. Okay, so I'll give a hint, but not right now. Okay, the main point here was that, I mean, you can think about these extra, these extra dimensions. I mean, sort of, they really correspond to when you really want to write down a small description. They correspond to new variables that help you express things with fewer inequalities. Okay, we'll rework exercise 1. Exercise 2 is very interesting. With a hint, it's not so bad, so I'll give a hint. But okay, let's keep going, because our goal was actually in showing that one cannot always do this for polytopes that we care about. So we introduced this the cut polytope. Okay. So I'll not say what the definition is again, but it's the convex hall of indicators of cuts in the complete graph. And what we said last time was, using this factorization theorem of Yannakakis, one can write this parameter, sort of the smallest lift of the cut polytope, as the non-negative rank of an associated matrix. Okay, and I'll remind everyone what non-negative rank is in a second. And what's this matrix? The matrix is the following. Okay, so it's indexed by functions and points. I'll say what the domain is in a second, but it's just the evaluation. I mean, this is the matrix where f is a non-negative quadratic function on the cube. So this family was the set of all non-negative functions on the cube which are quadratic. So such that f of x is equal to aij xi xj for some coefficients aij. So this is the class of all non-negative quadratic functions on the cube. And then x is just an element of the discrete cube. Okay? And what we argued last time was basically, I mean, it's just by definition, every such function is non-negative on the discrete cube. And the set of linear inequalities that the cut polytope sort of is able to prove, sort of the set of inequalities that are valid for the cut polytope, is essentially the set of all the inequalities of the form f of x is greater than or equal to 0. Okay. Okay. So our goal is to if we want to prove a lower bound on this extension complexity of the cut polytope, then our goal now reduces to proving a lower bound on the non-negative rank of this matrix. Good. And okay, so now let me remind you what is non-negative rank. So if we set, okay, so let's set R to be the non-negative rank, and then let's write the representation we had last time. So this means we can write f of x, which is just this entry of this matrix, as the sum with R terms, AIF times BI of x, where these AIs and BIs are positive functions. So the AIs are functions on these, they're coefficients assigned to every non-negative quadratic polynomial, and the BIs are non-negative functions on the discrete cube. Okay, so this is just I'm just rewriting the definition of the notion of factorization. So what we wrote before was that we can factorize the matrix like this, where both of these things are non-negative matrices of the appropriate dimensions. So I'm just gonna, okay, let me not write it. But if you rewrite this matrix multiplication, where these are the rows of the matrices and these are the columns of the B matrices, this is just an alternate way of writing this matrix factorization. And the rank is that there's a small number of terms in this sum. Okay? And what we said last time was a nice way to think about this is that we have a family of inequalities we want to prove. Okay, so this is more general, but we're just doing it for the cut polytope. Those inequalities are the set of all non-negative quadratic polynomials on the discrete cube. And you can think about this expression as a proof. By definition, all of these BIs are non-negative, and these coefficients are non-negative. So of course, if we can write f of x as a non-negative combination of these non-negative functions, then this is a certificate that f is itself non-negative on the cube. Okay. So I like to think about these as sort of axioms. You have a family of axioms, and then sort of your proof are the proof is the collection of coefficients here. Okay. So for any function, you could given any family of axioms, so for any function I can ask, say any non-negative function, I can ask, is there a proof using those axioms? And the question of the non-negative rank is just really, can you prove non-negativity of all these functions using a small family of axioms? This is equivalent. Okay. And it makes sense that this is sort of what would come up, because a nice way of thinking about a polytope is just sort of as an object which proves a family of inequalities generated by the defining inequalities. And one that has a small complexity basically means that it corresponds to a small number of axioms that can prove all of the inequalities that are valid there. Okay. So our goal is now to argue that if we want to prove a lower bound, that there exists some quadratic function that doesn't basically for every small set of axioms, there exists some quadratic non-negative function that cannot be proved with those axioms. That proves the lower bound. Okay. And we said even more last time. We said actually there's sort of a natural family of axioms we might try, which are functions that depend on only a few coordinates. Okay. So let me remind you also this definition, that a function, let's not call it f, let's call it q, is a k-junta if q depends on only k of the inputs. Okay, so there exists n minus k inputs, so if you change their value from 0 to 1 or back, they don't affect the value of q. And then we had this. So we defined some, some generators for this cone, but really what's important to us is the cone, which is this is the set of all non-negative combinations of non-negative k-juntas. Okay, so it's the set of all, you have some positive coefficients. The corresponding question, like sort of, if is a function in this cone, this is the question of, can I write the function as a non-negative combination of non-negative k-juntas? So can I write it as a non-negative combination of functions which depend only on small pieces of the input? And what we said was that actually this cone, well, the one right reason to consider it is that it's not too big. So by virtue of the fact that the functions only look at a small number of coordinates, the family, you can generate all of them using only n to the k functions. Okay. So the first question you might ask is, okay, and this is one thing, and also sort of this question is really, okay, I'll say it in a second. Let's say it now. Okay, so here we ask about a general proof system. Do there exist a small number of axioms that prove all these non-negativity assertions? Here's a specific family of proof systems. For every k, you get a set of axioms. Not clear what they can prove. Maybe they can prove, maybe they can certify non-negativity of all of these functions. In which case, the cut polytope would have a small lift. But there's a natural definition we can make here, which is to say for every function, what's the smallest value of k such that the k-juntas can prove its non-negativity? So this is the last definition we gave last time. The junta degree is the minimum k such that f is in the cone of k-juntas, the cone of non-negative k-juntas. And to connect this to what Eden talked about, this is exactly the minimum level of you don't have to know this, because it's a nice thing to say, of the Shirali-Adams hierarchy that certifies non-negativity of f. Okay, so so you can write down a program which basically, okay, let's just, it's not exactly clear what this means, but it's not so, we will not need it. Okay, I just hope the definition is clear. That this is okay. I hope the definition is clear, and maybe we can get some easy bound that the junta degree of f is at most n. That's easy because, of course, f itself is a representation as an n junta. Just an n junta is every function is an n junta. Okay, I guess if I want to say it that way, and I should say here, at most k coordinates. Okay, good. So now we get to the interesting part. Okay, so now let's show that these axioms are not very good. So we saw this last time. Let's define f of x to be the following quadratic. Okay, the sum of the input bits minus 1 squared. So here's a claim, and hopefully you guys will. Let's all prove it now together. That actually, this is a quadratic function that doesn't have any non-trivial representation as a sum of juntas. So I claim that any attempt to write this as a sum of k juntas for k less than n was going to fail. Okay, so somehow there's no local proof that this thing is non-negative. And did you talk about pseudo distributions in your sort of?
Yeah.
Okay, so we'll see in a second, but a different way of saying that is that there's some sort of pseudo distribution, a fake distribution, where when you look at every n minus 1 bits, it appears to be a real distribution, but on all n bits, it doesn't correspond to a real distribution. And under that fake distribution, this has a negative expectation. Sort of, that's, okay. Okay, we'll see it in a second. Maybe, I don't know why, there's no reason to jump ahead. Okay, so let's prove it. It has a very simple proof. So let's suppose, for the sake of contradiction, that f can be written as the sum of, say, a bunch of qi's. Each qi is a non-negative k junta. Okay. And in fact, let's just go all the way. Let's just say it's a non-negative n minus 1 junta. Okay, so it can depend on all the bits except for 1. Okay, so if the sum of the xi's is equal to 1, then, okay, f equals 0, right? Okay, good. And since all these functions are non-negative, it implies that in this case, sort of qi is equal to 0 for every I. A bunch of non-negative things sum to 0, they have to all be 0. Okay. So on the other hand, people do that on the internet sometimes. Okay. F of all zeros is equal to 1. But, okay, so now you guys can do the punchline. So let's prove that, but on the other hand, qi at all zeros cannot be equal to 1. So does anybody see how to prove it? Right, so there's at least one coordinate on which qi does not depend. Let's say, suppose it's the first coordinate, because or the last one, but otherwise it would have been more difficult. But it doesn't, of course, it doesn't matter. So if it's the first coordinate, just change that, change the first bit to a 1. The value of the function doesn't change, but now we're in the case when the sum of the bits is 1. So the function should be 0. Right? Okay. Well, this is a, this is a contradiction. I don't know if that means no parking, right? Okay. Does it make sense? Just, try to write f as a junta. If exactly one of the bits is equal to 1, then f is 0, so all of these things must be 0. But if every one of these functions doesn't depend on one of its coordinates, flip that bit to 1, the thing remains 0. On the other hand, sorry, let's say for qi, it doesn't depend on some coordinate. So take say it's the first coordinate. Yeah. So then we know that this is equal to 0, but we can flip this to 0 without changing the value of the function. So qi at all zeros is equal to 0. And this is a contradiction, because it cannot be that all the qi's are equal to 0 at the all zeros vector, because f is equal to 1 at the all zeros vector. So this is just a, okay. Yeah, I didn't say it was so this is not particularly profound, but this will be the basis for, in some sense, this will be the core of why the cut polytope doesn't have a small lift. Okay? Just because non-negativity of this function cannot be proved, can't be proved in a local way. You have to look at all the bits simultaneously to see that this thing is non-negative. Okay, so let's see a slightly different way to prove it. Okay, so yeah, okay. So let's look at the dual cone. Sort of, okay, you can look at this cone. This is a convex body. This cone of non-negative k juntas. So of course we know that if there's something which is not in the cone, then there's a kind of a unique way to show that it's not there, which is to give a hyperplane separating it from the cone. Okay, so I just want to describe what those hyperplanes look like. So let's say that a function, and this is exactly corresponding to the pseudo distributions that Eden talked about. So let's say that a function is k locally positive if the following is true. So we sum over all of the points of the discrete cube. We look at the value of the function there. Okay. So it's k locally positive if this holds for all non-negative combinations of k juntas. Okay. So in fact, there's no reason to. We can make this slightly a simpler statement, which is just to say that Q itself is a non-negative k junta. So for all Q that are non-negative and a k junta. So this function phi, it might not take positive values. It could take negative values. But if you try to figure out that it's taking negative values just by summing against a k junta, then you can't do it. It fools k juntas into thinking that it's positive. I mean, how would you show that a function is that this thing takes some negative values? Well, the obvious thing is just find the negative value and then just multiply it times if you took q equal to a delta function at some point where phi is negative, this would be negative. That's a nice certificate that this thing is not positive. But but the delta function depends on all the bits. It has to look at all n bits. So the function is locally positive, k locally positive, if you can't figure out that it's negative using only test functions that look at k of the input coordinates. Okay. This is the definition of k locally positive. And now here's the sort of dual characterization of this Junta degree. So I'm writing lemma, but it doesn't really require a proof, which is that the Junta degree of some function is more than d if and only if there exists a d locally positive functional phi that right. I mean, this is by definition, so okay. Anyway, but okay. There's a unique way to certify the fact that something is not a Junta, which is which is to find a locally positive functional and then test f against that functional. One direction is clear. It's clear that, just by definition, if this is less than 0, then f cannot be a d junta or a non-negative combination of d juntas, because if it were, then it should be greater than or equal to 0. The other direction is the separation I'm talking about. These are exactly, you can see these are exactly. If I look at the rays of the d juntas, because this is d locally positive, when I take the inner product of this function with those rays, I get something non-negative by definition. And when I take the inner product with f, I get something negative. This is the separation between, right, the picture is that the picture is like this. You have this cone of juntas. You have f sitting here. And I just claim that maybe in the statement of the theorem, this is d. And I just claim that there's a unique, how do you show that f is not there? Well, you find a separating hyperplane. The normal to that hyperplane will exactly be a d locally positive functional. These are just the description of all of the, of the separating hyperplanes that separate you from this cone. Okay, so this is, I'm leaving the lemma without proof, but this is just by definition and knowing that what the extreme rays of this cone are. Okay. So I'm just sort of, here we prove that the Hünter degree of this function f is large. And I want to say that in general, okay, we proved it by hand. This is sort of a, we can give sort of more convex proofs of these things. So here's a, and so the claim is just that there's only one way to prove that the Hünter degree is large, and that's to find something which is positive on all the Hünters, but is negative on f. Okay. Is there questions about it? People look confused? Yeah. So I mean, really, the only thing that we So I mean, this direction should be clear. If I have a functional where when I sum against f, I get something negative, but since this functional is d locally positive, when I sum against any d Hüntas, I get something positive. This says that I cannot write f as a non-negative combination of d Hüntas, because then I should get some positive. Every term should be positive. And then the other direction is maybe requires a little bit of thought, but once you've seen these things, should not be unbelievable that actually this is the only way to prove that a function cannot be written as Hüntas, as a convex combination of Hüntas. Those are exactly the dual functionals. Okay. So what I want to do is I want to prove this claim again using a k locally positive functional. Okay. So here's proof number 2. Of the claim. So we prove it. Okay, so let's define a functional. It's going to be, let's say, -1 if x equals 0. 1 if sort of if there's exactly one bit equal to 1. So if the Hamming weight is 1, then it's going to be equal to 1, and then it's going to be 0 otherwise. Okay, this is the functional. So it's not positive. Obviously, it takes value -1 at 0, but the claim is that no local function is going to be able to recognize that. Okay? So obviously a non-Hünter can recognize it. Just take the delta function at 0, or this f is going to be able to do it. So the first thing we should do is test it against f. So what do we get? Okay, there's only f is 0 on all these cases, so we don't worry about that. This is the only case when they're both non-zero. So this is -1. At 0, f is equal to 1, and this thing is -1. Okay. So that was, so we verified sort of this fact. Now we need what's left to do is to verify that this is actually a n-1 locally positive. So this thing fools all of the Hüntas. Okay. Good. So maybe the easiest way to do that is to remember that sort of this cone is what it was generated by. So we said that we can generate it using functions of the following form. So this is a function which just, okay, let's write the definition. It takes x as input. It looks at the bits of x on the set S and checks that they're equal to z. So it's 1 if x sort of, if I look at only the bits on the set S is equal to z, and 0 otherwise. So last time we said that these are exactly the, the extreme rays of this cone. Okay. So every non-negative k-junta can be written as a non-negative sum of these things. And so the point is, to check this property, to check that something is k locally positive, we just need to check it at these values, at these functions. Okay, so what happens if we evaluate it at such a function? Okay, so I guess this is really simple, right? I mean, if this z is non-zero, then this thing is just equal to 0. Because if this z is non-zero, this thing is, we want to prove that this is non-negative. So the only way to pick up a negative contribution is for this thing to be supported at 0, which means that this z should be equal to 0. If this thing is looking for a 1 somewhere, it's not going to be supported at 0. So in fact, the only case we have to consider is this is the all zeros vector of length k, but sort of just a function which looks at the bits in S and verifies and checks, are all those bits equal to 0? If so, the function has value 1. If not, it has value 0. Okay. Just the point is, if you look for any string with a 1, then it's clearly not going to have a contribution on the negative term, and so it's going to be positive. So what happens here? Well, I guess we get a negative 1. That seems bad for us. That's sad. Okay, so why do we get saved here? Okay, so this is a k-junta. So why are, hopefully we get some other contributions here. Otherwise we're in bad shape. We want to show that this is non-negative. Actually, let's just go to the, suppose this is a n-1 junta. That's the hardest case. So there's one bit on which it doesn't depend. Yeah, so the point is, there's one bit that's not in this set S. When we flip that, when we flip that bit to 1, this thing doesn't change value. So we get a 1. We get a 1 from flipping the one bit that this thing doesn't depend on to 1, right? This thing was at all zeros it gave us a 1, and there was a -1. So now just find the one bit it doesn't depend on, flip that to a 1. This thing changes to 1, so we get a contribution of 1. Okay, so we didn't prove that these are all equal to. Okay, for this one it is equal to 0, but for every other function here that we didn't have an all zeros pattern, actually it's non-negative simply because there are no negative terms in the sum. So this is the one case when we see any negative term and it's 0. So this verifies that phi is n-1 locally positive. Okay. So it's just it's a proof of the claim using a by. This was combinatorial, which you'll see in a moment is going to make, this is a kind of a nicer form of proof because we have a, it's doing things in a sort of convex way. But at the moment we just saw two proofs that there is a quadratic function that has large junta degree. Okay, so now we're set up to move on to the meat, which is how to use this function to prove that not only is this very specific family of axioms not sufficient to prove the inequalities we want, but no small family can prove all of these inequalities. And the way we're going to argue is basically that if there's a small family that proves all these inequalities, then essentially a family like this will prove all those inequalities, sort of by reduction. And then that would be a contradiction because we know that this family is not particularly good. Okay. Let me give one more. Let me give the second exercise. So everybody hopefully remembers the first one. Okay, so here's the second exercise. Prove that the Hünte degree of a g, which is a function that I'll write down in just a moment, is at least n/2, where g is the following function. So it looks very similar to what we did before. Okay, so here's another quadratic polynomial. When n is even, it's not non-negative on the hypercube. But when n is odd, there's no way that the sum of bits can equal exactly n/2. So the value in here must be at least 1/2, because you can only get within 1/2. So then when you square, you get 1/4 minus 1/4, which is 0. So the point is that when n is odd, on the hypercube, you cannot get this function to be negative. On Rn, you can get it to be negative, obviously. Set each of the bits equal to, set each of these equal to 1/2, it will be negative. But on the hypercube, this is positive for n odd. And the claim is that, there's sort of no local proof of that. You cannot prove it by looking at only small subsets of the bits. And this is a very interesting function because whereas, if you go from linear programs to semi-definite programs, the sum of squares hierarchy, so the Lasserre hierarchy, can prove non-negativity of this f up here very easily. In the first round, it proves non-negativity of this f. But the sum of squares can't prove non-negativity of this thing even in n/2 rounds. So I don't ask you to prove that, only that the Hünte degree is large. So only that Charlie-Adams cannot certify it. So again, and the statement is that this thing is non-negative on 0, 1 to the n, but the claim is that you cannot write it as a non-negative combination of functions that each depend on only n/2 bits. Okay. That's the second exercise. And yeah, and maybe I should give a hint, which is, so how can you make it, how could you pretend that this function is negative, right? These locally positive functionals, they're not positive, but they just pretend to be positive on Hünte's. So the way you would, if there was a way where you could, basically, if you try to set every one of these equal to 1/2, then this thing should be negative. So the key is to define a locally positive functional which pretends that every bit is equal to 1/2. But basically, you can think about a locally positive functional as a probability distribution, and then or as a fake probability distribution, and then it would pretend that every bit is 1 with probability 1/2. Exactly. Although, yeah, okay. So this is not a. I guess that maybe even that doesn't make sense. What it should actually do is that it should pretend that exactly n/2 bits are equal to 1. That's what it should this is what it's trying to do. Because then if this is n/2, then you get something negative. So a real probability distribution cannot do that. But the claim is that there's a fake distribution which cannot be found out by Hünte's that can pretend this thing is negative by pretending that exactly n/2 of these are set. Okay, that's the exercise, the second exercise. Okay, good. So now let's state the theorem we want to prove, and then we'll take maybe a short break. So now, okay, good. So we're going to prove that this function, which is just hard for to certify with juntas is actually hard for any small set of axioms. Okay, so to do that, let's do the following. So I'm going to use the letter G. It's not this G. It's some other G. But let's fix a function G on 0, 1 to the m. Okay, you should think about this. This is like a hard function for junta. So this function has large junta degree. And then let's define a matrix. Okay. So for n greater than or equal to m, and the matrix is going to be a submatrix of, okay, we erased it, but of the matrix we care about. Oh, here it is, sorry. It's going to be a submatrix of this matrix. And then we'll, and then the goal will be able to prove a non-negative rank lower bound on the submatrix, which also proves a non-negative rank lower bound on the full matrix. So for n greater than or equal to m, define the matrix in the following way. Okay, I'll say what the indices are in just a second. So this is a matrix. I just write it in this way. So it's indexed by sets of size m. So this is a subset of the coordinates of size m. And x, as before, just ranges over the elements of the discrete cube. Okay? So you fix a function on m bits. Like here's n bits. You fix a function on m bits, which is smaller than m. And then the matrix we're going to look at is just for every set of m bits, you can consider, for every set of m bits, you can consider the function g. I give you some input on n bits. Now I'll just evaluate the function g on the input, but restricted to the bits in the set S. So basically what I'm doing is just taking this one function and just kind of hiding it all over, well, not really hiding it, but just putting it all over this, The function is defined on m bits, but now the domain is on n bits, and the entries are just for every subset of m bits, evaluate the function there. So I'm just sort of like planting this function, right? We said this function is hard for juntas to certify. That's going to be our assumption. Then we define a matrix where we just plant the function all over the place. And the claim is that this gives us some kind of hardness amplification where now no small family of axioms are going to be able to certify sort of non-negativity of all of these restrictions at the same time. Okay, so and notice that if this function g is quadratic, on m bits, then m and g is it's a submatrix of our matrix Mn. Okay? Just because, this is if G is quadratic, then this is indeed a quadratic function on n bits. It happens that it only looks at m of them, but, okay? So the point is that, so this is the setup. We start with some G, define this matrix. If G is quadratic, this matrix is a submatrix of the matrix we care about. And then the claim is going to be that if the junta degree of G is large, then the non-negative rank of m is large. Okay, so say in terms of sort of the proof framework, if juntas cannot certify non-negativity of this G, then no small family of axioms can certify non-negativity sort of all the restrictions of G. Okay, so let me state that theorem, and then we'll take a break. And then our goal will be to prove it. So theorem, just a reminder, this is joint work with my co-authors, Suan Chen, Prasad Raghavendra, and David Storr from 2013. And the theorem is as follows. So for every G, and every n, in this case, let's say n is at least twice m, it holds that the non-negative rank of this matrix, which is just G planted on all the m-bit subsets, is at least a constant depending on G times n to the Hünte degree of G minus 1. Okay, so where this constant depends only on G. So you sort of fix a function with large Hünte degree, then you get a family of matrices whose non-negative rank is growing at least as fast. So as we said last time, this in particular implies that the extension complexity of the Cod polytope grows faster than any polynomial. Why does it imply that? Well, just for every exponent you want, just take G equal to to this f. Now it will be only on m bits, and so like okay, so there's a. But basically, for any exponent you want, we know we can find a G for which this is bigger than that, and then just plug in that G, you get that the non-negative rank grows faster than n to that power. So it doesn't show like exponential lower bounds, as we actually know are true from the work of Fiorini et al. But because of this dependence on G, but this captures the flavor of what one wants to do. And in fact, it is a non-trivial result, right? Like this. It wasn't, even the polynomial growth was a problem for 20, 25 years to prove. You can get exponential lower bounds, but then you have to be more careful. Okay, but our goal now is going to be to prove this theorem. So let's take when do we go to? 15 after? Okay. We can just do breathing exercises or something. Are there any questions? You can just. Okay, I'll start erasing. One nice thing, if you follow, so first of all, if you follow all 3 lectures, then it brings you up to sort of the state of the art in this area. And there are a remarkable number of open problems in the area. So for instance, to do this on any domain that's not 0, 1 to the n, no one has any idea how to do it. So for instance, if you wanted to do the same exact setup where instead of 0, 1 to the n, you took towards of the complete graph, it breaks completely. There's a sort of, or if you wanted to, for instance, do it for all the perfect matchings in the complete graph. In this case, non-bipartite. That would be great. That would prove a lower bound on the extension complexity of the matching polytope, which is known. But if it worked, it would likely also prove a lower bound on the size of semi-definite programs for the matching polytope, which is an open question. We don't know a lower bound on the semi-definite extension complexity of the matching polytope. But the point is that somehow this doesn't work on any domain except 0, 1 to the n. It should. It's just the techniques break. Just define okay, so just define the function to be a function on Tors. Right? If you extend it to everything, it would just must be negative. Yeah, but just like this one, right? This one, if you extend it to the Rn, it's going to be negative. Yeah, so it could be negative now on points of the discrete cube, sort of on 0, 1 points that don't correspond to Tors. But then there's all the definitions extend. There is a notion of what it means to be a Hünte. It's the rather obvious one. You look at only a small number of edges in the Tor to see. Okay, so sort of, yeah, all the definitions extend in a nice way. Well, you'll see maybe today, but definitely by the end, the place where we use the fact that it's 0, 1 to the n. But yeah, it's a little bit mysterious. Okay, and there's lots of other. If you read the notes, there's also an issue with if you try to make this if you make this quantitative, it's capable of proving exponential lower bounds on the non-negative rank, but it depends on. I mean, actually, you can see it here. Sort of, if you just want to prove a lower bound on the Hunter degree, you can use one of these k locally positive functionals. It turns out that if you want to do something more quantitative, you have to assume some smoothness property of the functional. Okay, like the functional isn't too big at any point. This. So when you get into these details, for instance, for like approximation problems, one can prove that no linear program can do better than a factor 2 approximation. No polynomial-sized linear program can do better than a factor 2 approximation for max cut. So this is so for max cut, linear programs cannot distinguish between the case when the max cut of the graph is very close to 1, it's almost bipartite, or when it's like a random graph and it's close to a half. Of course, for semi-definite programs can do it. Gomez-Williamson does it, within 0.878. But that only holds up to size n to the log n. It's possible that there are linear programs that do better, which are just slightly super polynomial size. It would be very, very interesting. Okay, so I mean, this is one of the issues that comes up. It's in the notes when you start trying to make things quantitative. Okay, there are lots of them, but okay. So let's at least say what the main idea of the proof of this theorem is supposed to be. Okay. So we'll assume that the rank is small and hope to derive a contradiction. So let's say that R is equal to the non-negative rank of this M and G. Okay. And then let's just write down again what this means. It means that we can write this matrix as a sum like this, where the AIs are, they're functions on subsets of size, non-negative functions on subsets of size M, and the BIs are, again, non-negative functions on the hypercube. Okay. So this is what it means that the non-negative rank is small. Okay, so and let's also now let D be the, okay, so now we have this hard function. We have this function G, which is, we presume that it's going to have large Hunter degree, so let D equals this. And let's now give a name to the, we know that the degree is large. Okay, we know it's bigger than D, so that means that there exists a locally positive functional. I want to use this functional, so so there exists a phi, which is D locally positive, and on the other hand, okay. Let me introduce one piece of notation here, which is just that I want to take expectations. So when I write expectation sub S, this is over a random subset of size M chosen uniformly at random. And when I write expectation sub X, this is over X just chosen from the hypercube uniformly at random. Okay, so I want to have these things. And so I just want to state the sort of the fact that there's a locally positive functional that proves this thing is non-negative. I want to state it in the following way. Well, I can't use this notation because that's over 0, 1 to the n, and actually g is on m bits. Let's write it this way. Okay. These are the properties we have. I interchanged sum and I changed sum to expectation, but actually, since we're not doing anything quantitative, there's no difference because it's just we only care about things which are positive or things which are negative. So the fact that I multiplied here now by 2 to the minus m doesn't affect anything. Okay, so we know that g has large, the Hunter degree is at least d, so there exists this locally positive functional. And now the last thing I want to do is I want to define phi s of x. This is going to be phi, but restricted. Remember, this is I guess I should write here. This thing is on m bits. So d locally positive. Okay. And then here's the definition. Phi sub s of x is just phi applied to the restriction of x. Okay. So now here's what I want to do. I want to say, basically, let's suppose something optimistic for a second. Let's just suppose that each of these BIs was a D-junta. Okay? Then I claim that this factorization cannot, that such a factorization cannot exist. Okay? So if each BI only depends on at most d coordinates, then, well, just look at what happens. If we take so now I'm going to apply this to sort of this thing to both sides. Okay, so I choose a random subset S and a random X, and I look at this phi s of X applied to the left-hand side. All right, so this is just, well, by definition, this is G actually like this, and actually by definition, this is also just, so by definition, this is just like this, and actually the S doesn't matter here. We're seeing, since we're going over a random X, this is just the same thing as if we choose y on m bits and look at phi of x, g of x, and our assumption was that phi is separating g from is negative on g, so this thing is less than 0. Okay. So just we planted g all over the place. I'm just saying that if you take this thing which is where sort of when I test it against g it's negative, then okay, if I test it everywhere it's just negative many times, so it's still negative. But now the claim is that if I apply this exact same linear function to the right-hand side, that I get something positive, under the assumption that each, we didn't use the assumption yet in this, but under the assumption that each BI is a D-junta, when I apply to the right-hand side, I get something positive. So that would show that if, there's no reason it's the case, these are just arbitrary functions, but if everyone was a D-junta, then we prove this factorization can't exist. And then what we're going to do next time is the main step, which is to prove that actually, given any such factorization with a small number of terms, we can approximate those BIs by juntas with a little bit of a twist there, thus proving the factorization cannot exist. So basically, we're reducing everything right now just as an approximation problem. Given these BIs, we need to get some property from them that follows from the fact that we're only using a small number of them. We'll approximate them all by juntas, and then that shouldn't happen. And it's just stress for a second why that shouldn't happen. So the point is, next time, we're really going to just be reduced to sort of an approximation problem. We have a bunch of functions. We want to approximate them by juntas in some specific way. But let's see that if they were juntas, this factorization couldn't exist. So when we apply this functional to the left-hand side, we get something negative. Actually, now let's apply it to the right-hand side, but let's just look at one of the terms. We're going to prove that when we do it on the right-hand side, it's positive. So we can just prove that it's positive at every term. We're happy. Okay, so on the right-hand side, if we just look at one term, it's something like, I'm just actually repeating the definition. It's this thing, take out the a sub I. Oops, that's not what the functional is. The functional has here this phi. Okay, so bi of x. Okay, so so does anybody see why this should be non-negative? If bi is in fact a d junta, why this should be non-negative? Right, so let's write one more line. This is just a restriction to S, and then here bi of x. So I want to say that if bi is a d junta, then this thing should be non-negative. And we should use the fact that phi is d locally positive. Okay, and we should, the only sort of even small technical thing is that this phi is a function on m bits, and we look at only some restriction. But the point is, if this is a d junta, right, I guess we can write it like this. Just take expectation over only the bits in S, phi of y, and then inside, and then inside we average over the rest of the, the rest of the thing. So this is the average over all x in 0, 1 to the n, such that x is equal to y on the restriction of bix. But now we're sort of in the, now we're this is a d locally positive function on m bits, and this thing, right? We said that if bi is a d junta, so this is a non-negative d junta. So by definition of a locally positive functional, this is greater than or equal to 0. Okay. Nothing. This was like really, I feel disingenuous to have written such a long. This was exactly what we said before. Just sort of the problem is that bi is defined on n bits, but if it depends on only d of them, then again we end up in the situation that we get something non-negative. Okay. So the idea is just that if we had a factorization where every bi is a junta, then then we derive a contradiction, because we apply this to the left-hand side, we get something negative. We apply it to the right-hand side, we get something positive, non-negative. Okay, so the last step, actually we'll stop now, but I'll write down what the last step is. This is the last step. So every one of those bi's we want to approximate by d junta, and then of course you can believe. If they were d juntas, we get a contradiction. Notice that we have a little room here, because this is less than 0, and how much less than 0 it is some possibly arbitrarily small constant, but it depends only on g. So there's a little separation that depends just on g. Okay, which that's why we'll be allowed to have an approximation, because actually the separation of g from this cone is it's a little bit of a fat separation. So we have a little room if we approximate to, we have a little bit of error we can play with. And I can just say that the approximation is actually going to be like some kind of, well, it's something like basically coming from machine learning. Basically, we're going to, we're going to, the point is, in what sense do we want to approximate B by this BI tilde? You could say you want some very strong approximation. You want it to be the same point-wise up to some small error. This would be too strong to get an approximation. Our notion of approximation is just going to be that, that against these functions, they behave the same way. That will be enough to prove a lower bound, because if these functions prove that these things are non-negative, and these two, and BI tilde are indistinguishable to those functions, then it will also prove that these are non-negative. So the approach is going to be like basically by like some kind of machine learning. We start with some hypothesis, which is like the trivial hypothesis. Then we say, is there a test on which our hypothesis is different from BI? If so, incorporate the test into our function. And then if now we pass all the tests, we're happy. If not, find another violating test, incorporate it. And by showing that this process doesn't run very long, we'll get an approximator that doesn't depend on too many coordinates. Okay, that's what we'll do next time. That's it.